Did I break it?
Yes. So I thought I'd start lightly by asking quite a simple question. How can we understand the entire universe? Well, of course, I'm not going to explain everything because, well, I don't think we can. Definitely not right now. But what I do want to point out and what I want to focus on is actually the concept of the universe, the entire universe. So how can we imagine, because that's the question I always get asked when I'm talking about millions of light years or billions of light years, how do you even think about these sort of distances? Why are you able to do this? And I'm hoping to take you on a journey and actually try and convince you that thinking about the universe as a whole is actually simpler than thinking about, for example, the solar system. So just to give a little bit more background, so some of you who might follow the news, a few months back, so in October I think this was, our simulation results, and our simulation is called Flamingo, got out, and we actually had quite some nice news about it. And it is at the moment, for now at least, the biggest ever simulation of the entire universe that was ever done. And to give a number to this, Flamingo simulated something which was on the order of about 9 billion light years. So probably at the moment you'll think, okay, what does that mean? And hopefully at the end you'll be like, okay, I have some idea for what 9 billion light years really means when you think about the universe. So usually when astronomers talk about light years or distances, they do stuff like this. So this is correct. So 1 light year is 9 and then, I don't know, a few zeros meters. And hopefully, just like me, you think this is pretty useless. And actually, looking at it like this, I think is pretty useless. I mean, you see that it's a lot, but you don't get much more of it than that. So let's move on to, so this is what I want to talk about. And then by the end, I'll quickly talk about how we use and think about these distances when we run our big simulations. So first, let's start sort of simple and start with the Earth. So this is a human, and since we're in the Netherlands, we're about 2 meters tall. So when we think about the Earth, which is, I took as a distance roughly, as a scale roughly 40,000 kilometers, how big is that compared to a human? Well, actually, well, not super funny maybe considering the last few years, but the human to the Earth is about as big as a virus to a human. Which, again, I would say, you know, it's a fun comparison, maybe also philosophically maybe, but it's still kind of useless, because you never see a virus, and also you rarely see the entire Earth, except if maybe one of you is an astronaut, but usually you don't look at the Earth as a whole. So, let's move on to the solar system. So, okay, wait, before I do that, so first, this is about 20 million times. So 20 million times bigger is the Earth, and smaller is a virus. So, if we now move on to the solar system, it becomes a little bit better, but still not great. So the Earth is about 0.1 of a light second, so light takes about 0.1 seconds to traverse the Earth. And if you want to get to Neptune, it takes about 4 light hours. So whenever we look at Neptune, we're looking 4 hours in the past, and light takes 4 hours to reach us. That's light hours. So in this case, we're looking at a difference of about 144,000 times bigger for the solar system compared to the Earth. So this is already better than the Earth compared to a human, but still a number where, I mean, also for me, I can't really imagine it. So if we move on, so if you think about that, actually, this is quite a fun comparison. So if you want to think, okay, the Netherlands is the solar system. If you then want to find the Earth in the solar system, then you have to look for roughly a postage stamp. So that's going to be quite a difficult search. Even if everyone in the Netherlands joins in, I still think it's going to take a while to find the one postage stamp that would represent the Earth. So, I don't generally think about planets. I think about galaxies, which, you know, the Milky Way is a galaxy, and usually you hear the Milky Way consists of about 1 billion stars, or a trillion stars. And actually, when you look at galaxies, so when you look at things like the Milky Way, it really starts to become a lot easier. So, for example, this is Andromeda, so that's about 1 trillion stars. Now, if you want to pack the Earth with 1 trillion people, then you would have to pack the Earth roughly like Tokyo. And then I don't mean the entirety of Tokyo, just the central area of Tokyo. So you would get roughly like a Star Wars-y-like planet. So already in fiction we can see that this is sort of possible. And also, even if you just look at a picture of a galaxy, so for a solar system you would have to put a postage stamp on the map of the Netherlands. So even if you take a really good picture, you're going to have a really hard time finding the Earth on that picture. But for a galaxy, you actually see that the stars, which is the blue and the reddish light, and also the gas, which is these darker regions, the dust, you can already see them. And actually galaxies, I would argue, also compared with the entire universe, are actually quite dense. So there's quite a lot of material packed in galaxies. So while the stars are very far away and there's a lot of empty space between the stars, when you look at the galaxy as a whole, actually it becomes quite dense. And if you would fly through a galaxy, you would find stars relatively often. So that's not the entire picture. So you might have heard about dark matter. And actually, our current theory of how things work, and of course there's some speculation about this, but in general it is quite accepted that any galaxy, so that is this little blue thing now, this is what used to be a very pretty galaxy, but now we've collapsed it into this little blue thing, has a halo around it. So kind of like an aura. Halo is more like the religious thing, which you have behind your back, but an aura, which is this sort of blob of dark matter, which extends way further than the galaxy. You can see the galaxy is in the middle here, and the dark matter that surrounds the galaxy, that actually makes up most of the mass of this system, is in an area around it. And actually it's about a factor 20 bigger than a galaxy. So usually, especially when we talk about the sort of simulations that I do, we don't really think even about galaxies, so to say. I mean, we know that there's a galaxy in the center, but usually we talk about what we call halos. So we talk about the entire system. So the galaxy and the dark matter that surrounds it. So at this point you can see, so the galaxy was quite dense, and actually the halo is also still quite dense. And there's only a factor of 20 between them. So we're already getting to a regime where things become a bit more imaginable. So when I talk about a galaxy and a halo, you can imagine it's just a little bit smaller in the center. Now if we go to the universe, just a little artist representation of here. So you might know this system, this is the local group. So you have the Milky Way, where we are, Andromeda and Triangulum. Now if you remove thinking about these little blobs of dark matter around it, it looks like it's quite empty. So you have the Milky Way over there, bunch of nothing, and then Andromeda. But actually, if you imagine also the dark matter at the same time, they're actually connected, and we're part of one bigger halo that connects the Milky Way and the Andromeda galaxy. So in that sense, actually also our local group, which is usually represented as being pretty empty, is actually also quite a nice, compact, complete system. And this actually gets even easier when you go to the entire universe. So here, so this is actually observation. So this is someone pointed the camera at the sky and put a little dot in any place where we see a galaxy. So you can see actually that if you look now, every one of these is a galaxy, so with its own halo. You can see that there's a lot of them. And actually there's not a lot of empty space left. And galaxies actually fill up a large part of the universe. And they form this kind of beautiful pattern that is the cosmic web that I can show even nicer with our own simulated image. So this is the results from the Flamingo simulation. And you can see that actually once you zoom out enough, you still have these structures along which galaxies are found and halos are found. But the universe as a whole is actually kind of homogeneous. So there's stuff kind of everywhere. In some places there's more, which are the lighter parts. This is where you'll find the galaxies and the halos. And then there's parts where there's a little bit less, which we call voids. So those are the empty regions in between everything. But as a whole, there's actually matter anywhere. So while the universe is quite empty, is usually seen as quite empty, I would actually say the opposite, where if you start thinking about the entire universe, it actually becomes quite filled with stuff. And so if you look at this, it's not quite the same everywhere, so it's not quite homogeneous yet, but it's getting pretty close. And usually what we talk about as the biggest structures, which you can see here as sort of these connected filaments, these structures that kind of connect up. The biggest structures that we still consider roughly like one thing are about 300 million light years across. Okay, so now we're back to stupidly large numbers. So what does this mean, 300 million light years? How do we put this in context? So to do this, we're going to compare the biggest structures, so this is about 300 million light years, with the Netherlands, which is about 300 kilometers. So it's easy. So every kilometer in the Netherlands is about 1 million light years in this comparison. So the first thing you may ask is, okay, how big is a halo? How big are these galaxies when you compare them to the Netherlands? Well, actually, if you look at this system, you actually find that there are like cities. So if the biggest objects in the universe are like countries, then the halos, the galaxies that populate them, are like cities. Which means that actually the universe is quite nice in that way. And you can even see it somehow as roads connecting these little cities where the galaxies are together. And this is kind of how I like to think about the universe. I think about cities being connected by roads, and when something is, you know, so a few kilometers away, they're quite close to each other. If something is, so in this case, a few million light years, but you can convert that to kilometers in this case, they're quite close. And if something is like hundreds of kilometers away, then yeah, it's starting to get a little bit distant. And if something is further than 300 kilometers, then it would be like a holiday to go there. So it's quite far away. So then comes the question, okay, we can think about this, we can see it in terms of the Netherlands, but the universe is not just halos. So just for a small funny comparison again, if you want to do planetary systems inside so if you want to see how big a planetary system is compared to these 300 million light years, then you get back to roughly a virus compared to the Netherlands. So again, pretty, that's a pretty extreme way of thinking, which I can do. So when we think about simulating the universe, actually what we do is we don't even try. Because we still have to solve, let the computer solve everything, and we're not going to be able to simulate viruses on the scale of the Netherlands. That's just too big of a range of scales, so it's impossible. So we don't try. And actually for the simulations we do, we use particles, so instead of just solving it, what we do is we split the Netherlands up in little balls, and then we see how the balls sort of evolve with time. And then in the end we can analyze how the balls are distributed, and then we get, in this case, this out. And if you compare the resolution of our simulation, so the size of the balls we use for our simulations with the Netherlands again, every ball is roughly the size of a building, a big building. So we can simulate cities still a little bit. We can know that there are cities, but we don't really get that much information about the streets or that sort of thing. We just know there's a city here, we know how big it is, but that's roughly what we can do. Okay, so now to get a little bit more technical, I want to describe a little bit about what sort of things we put into these simulations. Oh yeah, but before I do that actually, so this is a little part, of course, of the simulation. This is 300 million light years. We do 9 billion light years, so about 3,000 times larger. So actually compared to the map of the Netherlands, with that resolution, we do the entire Earth, which weather people, for example, don't really do. They usually do small parts. But we still do, compared to this, really big volumes, because because one of the things we are interested in, for example, is the things that are very rare. And so if you want to find stuff that is very rare, you need very big volumes to find a lot of things that are very rare. But again, on the Earth, you can still sort of make out the Netherlands, so that's the same in our simulations. So, okay, how do we do these simulations? Well, I was talking about one of these little resolution elements before, one of these pixels, so to say. But actually we have 3. Well, we have a few more, but these are the 3 most important ones. So we have gas, which is like on Earth gas, but also in galaxies you saw the dust lanes. Those are also what we call gas. And they follow sort of the same laws of physics as the gas in this room. So we do that, we simulate that. Then on top of that we have stars, which we form from the gas. So when the gas gets very dense, we can get stars. And then also, which is very important, we have dark matter, which, like I was saying before, it's actually not just for galaxies, but for the entire universe. Dark matter makes up most of the gravity, so most of the gravitational matter, is how we would say it, in the universe. So we really need the dark matter to make sure that everything collapses nice and easily. Now, our gas is roughly the size of a town, and our stars are also not one star. Actually, every resolution element of a star is about, well, about 1 billion stars. So one of the big challenges, which is what I personally worked on, is actually to make sure that all these things couple to each other, so all these things talk to each other in a way that is realistic. So one of the ways I already talked about is that gas, when it goes to high density, so for example when it contracts into a galaxy, so it gets nice and close together, then we don't form stars, because again, a star is like a virus, right? The sun is like a the size, well, way smaller even than a virus on the scale of the Netherlands. So we don't do that. So instead we put in a model by hand that when gas reaches very high densities, it gets turned into stars. At the same time, which is another thing, this is one of the things I worked on, when there are stars, especially when you have billions of stars, you know, probably most of you know, that when the very biggest stars in the universe, they explode after a while. So they turn into supernova explosions. And actually for our simulations this is very important, because if you just have gas falling into a galaxy, then at some point your galaxy is going to get way too big, because it just gas keeps pouring in and it keeps getting bigger and bigger, and it goes to high density, you keep forming stars, and it's just unrealistic. That's not what we see. So what happens is when you form stars, they actually explode. So not all of them, but a part of the stars, of the billion stars, explodes and then pushes back out the gas. So you get these explosions in the simulation. And I'll show a little video of that as well. So this is just a simplified view. Of course, there's a bunch of other things going on, including also black holes that do a similar thing. So a black hole grows by eating gas, and then it sort of explodes, and it pushes energy back into the gas. And in that way, you get sort of a regulating system. So if you put all of that together, so you put your nice little model together, you put it in a supercomputer, so this is the one we use, which is in the UK, in Durham, Cosma. Then you put in some things you know about the Big Bang, so how the universe looked early on. Then you can get the biggest simulation of the universe out. So we start from roughly the Big Bang a little bit later, and then the computer calculates for a long time, and then we see how the universe would look like today according to our model. So to end, I want to show a few videos. So this is the entire simulation. So here you see roughly the Netherlands in terms of the size, and here you see the entire simulation. And even though, because at this scale it's very much homogeneous, like I said, everything looks kind of the same, but you slowly see that the cosmic web, that this structure is forming, and that gravity is pulling stuff together. And as you see, so time is moving forward, now we're actually already quite there. What you see here is on this scale, so when you even look at the scale of the Netherlands, you see that it goes from being very much spread out to being nicely squished, but still not much changes. It gets a bit more interesting when you look at a single city, so at a single halo, which I show here. So there's the dark matter here, and then also there's just the gas here. And here you see that everything, gravity is pulling everything together. And actually, if you have a very clean eye, you can also see that there's these blast waves going out. So there's these supernovas are exploding, and also the black holes are putting energy back into the medium. And here you can see actually what's happening. So you see all these little fragments are falling together to form this very massive cluster of galaxies. So I don't know exactly how big this one is, but you can imagine that there's about 100 to 1,000 galaxies in this object. So this is really a city like Amsterdam or like New York. It's like a really big cluster of galaxies where there's lots of stuff happening, lots of stuff falling in, and also there's lots of galaxies here. You can even see them here, so the little dots are all little individual galaxies that are falling into this bigger halo of dark matter. So then I have one final video, which is roughly the same. So here you can see again, you have the stuff falling in, and you have these explosions going off from the supernova and the black holes. And mostly what you see is just gravity pulling everything together and creating these massive clusters of galaxies. Yeah, so I'll just let the video play. I think this is quite a nice one. You see a very big cluster forming here, and then there's actually also something forming up here, which is going to start moving together and form a really big single structure. And you can see also that in these clusters, so the brightness here is temperature, so you can see that it gets really hot at the center. As gas falls in, the pressure is really high, so you get really, really high temperatures. And these are both taken from our simulations, the ones we did here, and well, we did them in the UK, but we worked on them here in Leiden. Yes. So with that, I hope I convinced you a little bit that the universe as a whole is kind of easier to understand than the solar system, at least when it comes to scales, and I'm happy to take any questions.
Any questions for Roi? Yes.
So when you were preparing the model, you didn't inform it what the end state should look like, right?
No, we do. So there is a part of it, this is what we call calibration, because these simulations are quite complex, so there's a lot of things going on, and if we don't look at the solution, so we didn't do a big simulation, we did a very smaller volume. So actually about the size of the Netherlands is what I used most of the time. And then you put in the models and some of the parameters of the model, so some of the numbers that go in there, and you sort of tweak them a little bit until you find something that looks realistic. And there's a few things we can look at to make sure they look realistic. For example, we want to make sure we get the right amount of galaxies out. So that's one of the things I looked at a lot, to make sure that once we run the really big simulations, which took about a month to compute on a big computer, that it was realistic. So we knew beforehand that it was going to look somewhat realistic. But then we didn't have these very rare objects in those smaller simulations. So those are predictions.
Have you compared what the simulation produced versus what we know about the universe?
Yes, yeah. So that's why these simulations are so interesting.
Okay.
Yeah, because kind of the way I like to think about these simulations is they're one way to really test our models for physics in general. Which means that once we have the simulation, we can compare them with what we see, and in that way inform where we know what we're doing and also what we don't know what we're doing. So that's why we do these sort of things, yes.
Yes, over there in the back.
Yeah, is two questions. One is the expansion of the universe included in your model?
Yes.
And the second is, what is the time scale of what we have seen, if time means anything?
Yes. No, both very good questions. So, yeah, actually I'm cheating a little bit here with these simulations, with what I'm showing here, because this entire thing you're looking at is actually expanding. But if I would do that, then it would start off like this, and it would end up probably outside of the board. So you cannot really look at it in a nice way. But especially for how gravity works and other things, that's very important, so that's included. And then your second question, so this is the entire lifespan of the universe. So it's from roughly 13.7 billion years.
Okay.
It's a little bit less, but it's from the start to the end. Yeah, to now.
Yeah, then the other question.
You mentioned these rare objects. What kind?
So galaxy clusters, in just the ones I mentioned, because one of the statistical things you get with these simulations is that if you want something that is very dense, so where a lot of objects are coming together, then that becomes very rare, because it's very easy to create. So the universe is sort of homogeneous, but then it starts collapsing, right, because of gravity. So if things are not very dense, so not very big in terms of their mass, then it's very easy to get them, because the universe is homogeneous. But if they're very far away from the homogeneous universe, so these galaxy clusters, they become more rare. And that's why we need these big volumes. I hope that answers your question.
There's another question over here.
Yeah. You mentioned that from gas you go to stars, supernovas, then explode. And you also mentioned something similar with black holes, but black holes don't explode like supernovas, so it's like Hawking radiation, or what do you include in there?
So, Veronica mentioned quasars, for example, at the start. So when a black hole is accreting gas, so when gas falls into the black hole, not all of the energy of that mass goes into the black hole. So a large part of it gets swallowed, but also because for material to fall into a black hole, it needs to go it falls very quickly. So that releases a lot of energy. So that's the energy I'm talking about. So it's just sort of light or radiation or sometimes even gas flows that happen when gas falls onto a black hole. And at the centers of these galaxies and galaxy clusters, these black holes can be huge, like also the one Veronica talked about. And if a black hole is very big, this energy can be really a lot. Because, yeah, for stuff to fall into the black hole, it's going to accelerate a lot to get there. So that'll give it a lot of energy. And some of that energy will not go into the black hole, but it will be put into the gas around the black hole. Yeah.
Last two questions, so maybe here.
Yeah, because in your simulations you have to put in certain models for how the material behaves.
Yeah.
We know for a gas the properties and how gravity attracts it and how it heats up by compression and explodes again and it's supernova. But I think a very important part of your simulation is the dark matter. And what assumptions have you made for the dark matter? We know it has gravity, but we don't know anything about how dark matter clusters and how it dissipates energy to get together. So,
Yeah.
what have you done there?
So, yeah, so the thing is, we don't really know what dark matter is. So, what if is it a particle or but actually, we do sort of know how it clusters. So, when we start the simulation, so, oh, that's the wrong way. Let's see if I can. So, this is how the simulation starts. We actually know how to put the dark matter here. We can not observe that directly, but from the influence of the gravity of the dark matter, we can make an estimate of how the dark matter is distributed. So we do have an idea for that. And then the only other assumption is that gravity affects dark matter. And that's the only thing it does.
And it has to dissipate some energy to cluster together. So,
No, that's the thing. That's also why the dark matter doesn't go into the galaxy, but it stays around it. So it falls together. But because it cannot radiate away the heat, because it cannot lose energy,
yes.
it stays in these larger extended halos around the galaxy. So it doesn't have to cool for that. It just has to fall in, and then it starts circling around itself, essentially. So we don't have to assume anything for that. That's actually only the effect of gravity. So it collapses, but then there's a sort of sphere you're left with that it cannot contract further. So if dark matter could cool, like gas, so if it could lose energy, then it would go to the same level as the galaxy. So it would become smaller, smaller, smaller. But because dark matter...
That's the point, yeah.
Yeah, but dark matter doesn't do that.
Yes?
Because it only has gravity. So it stays in this larger thing that is 20 times bigger than the galaxy. And actually it cannot do anything from that point. It will just stay in that state forever, in a sense, because it doesn't lose energy.
So the large scale primordial distribution remains more or less the same?
Yes, in a sense, yes. So it, in some scales it stays the same, but it does form these halos, which are not there at the start. So it falls into these large halos around galaxies, and that's where it stops. But it doesn't really evolve much more than that, except that, of course, dark matter from farther away in the end also gets pulled in. But it's only gravity that you need for that.
We need to move on to the next question. There was a last question over here.
Does dark energy play any role in these simulations? And if so, can you use the simulations to test different models of dark energy?
So yes to both. Even though not really our simulations for the different dark energy ideas. But when you do the expansion of the universe, when you take that into account, you have to include dark energy, at least for our current way of thinking the universe works, even though we don't know what dark energy is, but we do know that we need it for the universe to accelerate. And that acceleration is taken into account in the simulations. So one thing that you can do is change this model, so have it not just be an accelerating thing, but have it do something slightly different. And then you can run a similar simulation and look at what the differences are between the simulations.
And has that been done?
What?
Has that been done?
Yes, that's something that people are working on. Yeah, we're not with this project, but we also have a project that is looking at those sorts of things. But usually the differences are quite subtle, so that makes it difficult to really pinpoint it, especially when you're looking with a real telescope. Then you have to find these differences also there, and that is very tricky.
Yeah.
Okay, so let's give Roi a last round of applause. We're gonna have now a 10-minute break, so feel free to go to the bar, grab some drinks, and then when you're back, prepare your phones because we're gonna start with a quiz.